My name is Emanuele Di Lorenzo from the Georgia Institute of Technology, and today I will discuss a talk about the multi-year persistence of the 2014-15 North Pacific marine heat wave. During the winters of 2014 and 15, the North Pacific experienced one of the largest extreme temperature events ever recorded. In the winter of 2014, over the entire Gulf of Alaska, this large anomaly developed and was termed the warm blob. And then the following winter, the anomaly had moved to the coast, here along the California coast and Gulf of Alaska, and also reached extreme temperatures in excess of 3 degrees C. So the main question of my talk is what dynamics led to the multi-year persistent warming between the winters of 2014 and 15. And in particular, I'd like to diagnose the forcing dynamics of the warm anomaly pattern and identify the large-scale mechanisms linking the warm anomaly patterns from one winter to the following winter. With that in mind, I will begin by trying to measure the size of these anomalies using simple indices that are the box average temperatures in these regions, which I'll refer as the Gulf of Alaska, and here is plotted, and in this region here, which is along the North American coast, I will refer to as the CCS or California Current System. If we look at the time series of these indices in the Gulf of Alaska, we find again the strong event in 2014 here, and then in the California one, we find the event to peak in 2015. And in both cases, you can see how these are extremes with respect to the variability recorded from 1980 to present. So the first question is, what forced the warm anomalies in 2014-15? I want to start with the pattern of the Gulf of Alaska, or warm blob, that emerged in 2014, and this was linked to an anomalous atmospheric pattern, which is shown here as a sea level pressure anomaly, and in particular the presence of what was referred to as the strong resilient ridge, and this was a post on a blog of Daniel Swain. Now, many studies have identified this ridge to be an important driver of this warm anomaly. And in fact, this can be seen by taking this sea level pressure anomaly pattern over the North Pacific and defining an index of the variability of the sea level pressure, which is plotted here. If we look at this index of sea level pressure variability associated with variability of this specific pattern in the atmosphere, the 2014 event was not of particular note with respect to other events that had stronger amplitude. But what happened in this particular year is that the atmosphere was persistently hitting the ocean with this anomaly, and that is what grew this warm event over the period of the winter. To see that, we can use a simple autoregressive model of order 1 to model the sea surface temperature variability in this region. This simple model shown here states that the rate of change of the sea surface temperature is equal to a forcing term, which in this case is our sea level pressure index, minus a decay term, which is the dissipation of the SST anomaly, with a time scale of the dissipation here set to between 8 to 12 months. And this type of very simple autoregressive model, or one-dimensional model of the sea surface temperature, has been used in previous studies to model the oceanic response to atmospheric forcing in this region. So what we're going to do now is we're going to take this pressure index of this particular resilient ridge pattern and apply it through this AR1 model to reconstruct the sea surface temperatures, which is shown here. And you can find that there's in fact high skill in reconstructing the historical evolution of the temperature in the Gulf of Alaska, including this high warm event in 2014. So with that said, we can say that this resilient ridge was indeed consistent as the atmospheric driver of this anomaly during 2014. So the next question is, what about the 2015 pattern of anomaly? Well, the question then is, are these anomalies in 2015 also consistent with direct atmospheric forcing, or is this just a residual of the ocean circulation advecting the anomaly at the coast? Well, we can look at the atmospheric anomaly pattern during the winter of 2015, and again, these are winters in the northern hemisphere defined as January, February, March. And again, we can make an index of the sea level pressure anomaly pattern, which is shown here. And if we look at this index, we find that actually in 2015 there was a big anomaly also in the atmosphere that is right here. We can also apply the autoregressive model of order 1 to reconstruct the temperatures index, and we find that indeed it has a high scale, of correlations of 0.82 and captures this very high event in 2015. Now the difference being that in this particular case, it was this very big event in 2015 that pushed the anomaly so high, whether in the previous case we had that persistent ridge hitting the ocean over and over again. So with that said, we can say that also for the 2015 event, it was the atmosphere that is consistent with driving this anomaly rather than purely an oceanic advection signal, which is also found in other papers that I am not citing here. So with that said, then we find that these strong sea surface temperature anomalies in the winter of 2014 and 15 seem to be driven independently by atmospheric forcing. And so the next question then becomes, how are the 2014 and 2015 anomaly linked dynamically? To address that question, let's go back first to look at our indices and ask whether statistically there is a lead-lag relationship between this pattern and that pattern. And so we're going to compute now a cross-correlation function between this index and this index, but in doing so we will remove the 2014 and 15 anomaly to see if there's a recurrent relationship aside from this very strong event. This is the cross-correlation function between the two indices. At lag 0 we find strong correlation of 0.7, and that's related to the fact that the indices are not defined independently. But if we now look at the cross-correlation functions at different lags, and here it's plotted in months, we find that this function is not symmetric, and we find a strong significant correlation at 12 months when the Gulf of Alaska pattern is leading the CCS. So from a statistical point, then there is a statistical correlation between this pattern occurring one winter and this pattern occurring in the following winter. So now we want to ask the question, what climate mechanism links these two patterns from a dynamical standpoint? To do that, we first recognize that these anomaly patterns that we saw in 2014 and 15 resemble very closely some recurrent pattern of climate variability associated with the two dominant modes of North Pacific variability. In 2014, the patterns look like the North Pacific gyro oscillation pattern, which emerges as a second dominant EOF of sea surface temperature in this region, whether in 2015 it resembles the Pacific decadal oscillation pattern. If we toggle between the actual NPGO and PDO canonical pattern and the ones that I just showed you for 2014-15, you can see the resemblance of the pattern. This is important because if we look at the NPGO dynamics, and in particular to the atmospheric forcing of the NPGO, which is shown here as a sea level pressure anomaly map during the winter of the Northern Hemisphere, January, February, March, we find that this is characterized by a cyclonic low-level pressure here close to the tropics with this kind of signature of weakening of the off-equatorial trade winds. The weakening of the off-equatorial trade winds will reduce the evaporation locally, and this reduction in evaporation will warm the SST. Now the warming of the SST will further reduce the winds, and in that way we generate a positive feedback, which is also known as the wind evaporation sea surface temperature feedback, or WESS, and this is work by Shangping Si. Now once you have this coupling between the ocean and the atmosphere through the WESS, this anomaly tends to migrate meridionally towards the equator, and for that reason this type of mechanism of coupling has been referred to in the literature as meridional modes. Now what happens is that during the spring in the Northern Hemisphere, April, May, June, this warm anomaly spreads into the equatorial regions. And once it reaches the equator, it has the ability to trigger an El Niño response, and this is work done by these authors over here. And with an El Niño response in the tropics, you shift it to atmospheric convection with high sea level pressure in this region and low sea level pressure in this region, and you excite planetary Rossby waves in the atmosphere that bring the ancestral connections back into the extratropics, and you can see here the following winter sea level pressure anomalies. And these type of anomalies in sea level pressure are well known. They project onto the Aleutian low and drive an SST anomaly that has the shape of the Pacific decadal oscillation pattern. And you can see it here with this anomaly at the coast. And so if we look at this transition from one winter here with this kind of warm anomaly in the open ocean the meridional mode dynamics, the answer response, and back to the extratropics with the PDO-like response that has now an anomaly that shifts to the coast. So we go from the open ocean pattern to the coast. And this is, again, is very similar to the evolution that we saw in 2014-15. And let me just toggle back and forth so you could see the resemblance of pattern. Now, the only difference or marked difference between these evolution is that the El Nino in 2015 was actually not that strong. And in fact, some people refer to it as the failed El Nino. And so the question I'd like to ask now is, was the ENSO teleconnection important in persisting and intensifying the 2015 anomaly in this winter here? To address that question, we will look at the sea surface temperature anomaly of this CCS pattern here, or PDO-like pattern if you like. And we're going to try to reconstruct that using an ensemble of 50 simulations with the climate model, with the goal to extract the fraction of the warm anomaly that originated in the tropical Pacific. And we do that essentially by prescribing time-dependent sea surface temperature in the climate model just in the tropical region, and then look at the extratropical response in both the ocean and the atmosphere. And so if we did that, we look at the ensemble mean of these 50 members, here plotted in black, we find that we have significant skill in reconstructing these temperatures. And the skill is about correlation of 0.56. And this is not surprising because ENSO teleconnections to this particular region have been documented in a lot of previous studies. And in particular for the 2015 event, we find that it accounts for about 1.5 degrees C of the 3 degrees that we had. We could also look at the spread of the model reconstructions for the 2015 events, which are shown here as a distribution. And these are in units of standard deviation, but the ensemble mean is right here, and it's about 1.5 degrees C. And here's the observations of 3 degrees. So you can see that the observations fall within the distribution of the model. And in fact, the model had a lot of members that predicted a very strong response in the North Pacific, indicating perhaps that the atmosphere was particularly susceptible to being excited in this teleconnection pattern, even though the SST anomaly of El Nino was not particularly strong. So with that said, we can go back to our diagram here, and we can say that about these ENSO teleconnections accounted for about 50% of the sea surface temperature anomalies in the following winter of 2015. So with that said, I'd like to summarize this talk with the large-scale dynamics of the warm blob in 2014-15. So in the winter of 2014, we had this atmospheric resilient ridge that generates the warm blob in the winter. The anomaly patterns in the wind also excite these meridional modes, and therefore this west thermodynamic feedbacks, which in the subtropics energize the ENSO-type response. Once you have the ENSO-type response, you have ENSO teleconnections that reinforce and add persistence to the blob in the following winter. And so this chit-chat from extratropics to tropics to extratropics is likely a key mechanism to add persistence to these anomalies in the extratropics, in particular the warm blob. Now what's interesting, this paper is documented in Di Lorenzo and Mantua in 2016. But what I wanted to say that there's also some interesting follow-up studies that show, for example, an increased persistence of these warm anomalies, or a coupling between this anomaly pattern and that anomaly pattern in the winter. And this is studied by Joe and Di Lorenzo. And this increased persistence is found also in climate model simulations under anthropogenic forcing, suggesting that a warmer climate could lead to an increase in the persistence of these anomalies. Now the question is, why would this persistence increase? And a study that just came out last week by Liguori and Di Lorenzo showed that the increase in the warm state of the extratropics and the tropics essentially intensified the thermodynamic coupling that excites these meridional modes. And so both in observations and in climate model simulations, we see a trend in the variance of the meridional mode. And if this trend increases, this may explain why this coupling between the two North Pacific mode also increases as this link becomes stronger. If you want to find out more about these studies, there's 3 papers that come out recently, and these can be downloaded at ocs.us. And with that, I want to thank you and conclude my talk.